Good evening to all. I hope that you all stay healthy and safe. I am Saravana Kumar, Assistant Professor in the Department of Mechanical Engineering. It is a great pleasure for me to share a few words about my college and our department. Francis Xavier Engineering College is located at Tirunelveli City and it was established in the year 2000. Francis Xavier Engineering College is the educational wing of SCAD group of institutions. Our institution has been offered autonomous status in the year 2019 for the period of 10 years. We offer 6 UG programs, 10 PG programs, and we have scholars carrying out doctoral studies at our research center. We have got gold category for Industrial Linked Technical Institute, which was awarded by AICTE CIA survey for 2 consecutive years. Our institute has received more than 15 million Indian rupees as a grant from various funding agencies DST, AICTE, MNRE, ISRO, DRDO, etc. for research and consultancy. Our institute has been selected by AICTE as a well-performing mentoring institute to cater the mentoring of group of colleges under Markadarshan scheme with a grant of rupees 15 lakhs. The Department of Mechanical Engineering is the largest department on campus with 600 plus students, experienced faculty members with good infrastructure facilities. We offer BE in Mechanical Engineering and ME in Industrial Safety Engineering. The UG program is accredited by NBA, the National Board of Accreditation. Our department is permanently affiliated to Anna University, Chennai. Apart from course-defined curriculum, we offer a number of value-added courses on mechanical software and impart various skill training like design and fabrication of car, bike and bicycle. In addition to well-equipped laboratories that comes under curriculum, we have a few special labs for encouraging innovation and new product development. We also have a strong academy for training students to appear for GATE exams. Our department has signed many MOU with leading manufacturing and service industries. We also offer international certification program on Fanuc CNC programming, computer aided design, non-destructive testing, and BMW Hyundai industry associated laboratories. Our students are actively participating in many technical competitions, winning prizes, and add glory to our department. The research area of our faculty members are bioenergy, combustion, solar desalination, green manufacturing, waste heat recovery, biomass gasification, and composite materials. I hope this session will be more useful for all of us. With this introduction, I welcome all the participants for this session and hope we will have a great learning today. Thank you.
Hello everyone, a very fine evening to all. I am Ayana Raja, Associate Professor in the Department of Mechanical Engineering. On behalf of Francis Xavier Engineering College, I would like to extend a very warm welcome to all the participants of today's event. I am so glad in introducing our honorable speaker, Dr. A. Valanarasu. He is a knowledgeable person who endlessly worked for the betterment of the society and became the most distinguished and successful professor. Presently, Dr. A. Valanarasu is working as a professor in the Department of Mechanical Engineering at Tyagarajar College of Engineering, Madurai. He obtained his bachelor's degree in Mechanical Engineering from Tyagarajar College of Engineering, Madurai, and master's degree in Thermal Engineering from CEG campus, Anna University, Chennai, and also completed his PhD from Anna University, Chennai. He has gained first rank in master's degree program from Anna University. He completed his BDF in Energy Storage with Phase Change Materials at National University of Singapore under Boycast Fellowship from Department of Science and Technology, DST, Government of India. His area of research is thermal energy engineering and he has more than 25 years of teaching experience. He has published more than 50 technical papers in international journals, also presented his work in many international conferences. He has carried out several sponsored research projects and consultancy works. He has authored books, that is Turbomachines, Thermal Engineering and Thermodynamics. He is listed in Marcus Who is Who in the World at 2009. He has received a national award for Best Teaching Faculty from Dr. Kalam Educational Trust for Tribal in the year 2017 and also received an International Research Ratna Award from Irjula and World Research Council for Best Researcher in Nanofluids in the year 2019. He is a reviewer for several journals in Elsevier, Springer, and Wiley, etc. Finally, he is also a fascinating individual, and we are happy to have such a renowned professor with us today. With this introduction, I welcome Dr. Valanarasu sir for the event, and I hand over the session to him. Over to you, sir.
A very good evening to one and all. Let me first thank the principal, head of the Department of Francis Xavier Engineering College, Tirunelveli, for giving me this wonderful opportunity to meet you all through this lecture. My special thanks to Mr. Yanar Raja for arranging for this webinar. And this webinar is on nanofluids and solar energy utilization. Let me first tell you the necessity of this nanofluid. A nanofluid is actually a heat transfer fluid. Uh, we are using many heat transfer fluids, but the reason why we need nanofluid is that the demand for heat rejection or cooling is increasing day by day due to the trends in faster speeds in multi-gigahertz or due to miniaturization like micro electromechanical devices and more power output from engines and transportation, and then brighter beam for the optical devices. So the system size is getting lesser and lesser, and the demand for the cooling is increasing higher and higher. So we have already implemented certain technologies to augment this heat transfer in order to improve the effectiveness of this heat transfer process, heat rejection process. Some of them are utilization of fins, which are the extended surfaces. Those who have studied or knowledge on heat and mass transfer know, right? The fins, the extended surfaces, which increases the convection heat transfer. The other technology we used is convection. So where we can increase the convection rate by increasing the velocity or the flow rate of the fluid, or even by changing the fluid with the high specific heat fluids like replacing air with water, or by increasing the flow rate, as I said, the velocity, we can increase the rate of heat transfer, again, convection rate of heat transfer, or the heat rejection rate in total. But increasing the velocity or the flow rate requires higher capacity pumps or fans, so which in turn increases the size and cost of the unit. So the available technologies so far have being used to maximize the heat rejection rate, but still there is some room or scope for improving this heat rejection rate further, uh, because in any heat transfer process industries, we use heat transfer fluids like water or oil or ethylene glycol, and these fluids, so they have very low thermal conductivity compared to solids. So that is how this concept of this non-fluid came in. So why don't we increase the thermal conductivity of the fluid? Because each fluid has its own thermal conductivity. So dispersing, by mixing some solid nanoparticles having high thermal conductivity in base heat transfer fluids, we can increase the rate of heat transfer. Because when conductivity is increased, the heat transfer coefficient is increased, and ultimately the heat transfer rate is also increased. So to overcome the poor thermal conductivity of the conventional heat transfer fluids, nanoparticles, solid particles having high thermal conductivity is dispersed in base heat transfer fluids. And so that is how this concept of nanofluid was evolved. But this concept of dispersing or suspending solid particles in, say, fluid is not new technology. The nanofluid concept itself is 2 decades old. And before we use the nanofluid, we mix larger size particles, like micrometer size particles, or some millimeter size nanoparticles in base heat transfer fluids. So the concept of dispersing solid particles in base fluids can be traced back to Maxwell period, the 19th century, where these solid particles of larger size uh, were mixed in fluid, base fluid. But there are certain drawbacks. Okay, so this slide you can see the thermal conductivity of solid particles like copper, gold, silver, aluminium. Okay, this metallic particles and non-metallic solids like diamond, silicon carbide, silicon, metal oxide like aluminum oxide. Right? And lastly, we have this heat transfer fluids, conventional heat transfer fluid, water, ethylene glycol, engine oil. See, the fluids, heat transfer fluids have inherently very low thermal conductivities compared to solids. So by adding this particles, solid particles having high thermal conductivity in this heat transfer fluid, the effective thermal conductivity of the fluid can be increased. Okay. As I said, this concept of this feasibility of the usage of solid particles in basic transfer fluid was investigated by several researchers previously. Some drawbacks with those technology or method, because the particles are of larger size, millimeter or micrometer size, the particles settle quickly. Okay? So it forms a layer on the surface, thereby it acts as a barrier to heat transfer. The heat transfer capacity is reduced. And to overcome this settlement, we increase the rate of fluid, but this increase the erosion of the heat transfer surfaces, because these particles are of larger size. So these particles, when they uh, slide over this heat transfer surfaces, the walls of a pipe or duct, resulted in erosion of the surfaces. And moreover, we could not use this suspension or this mixture in very small cooling channels like narrow channels, micro channels. And moreover, the pressure drop of this fluid is higher because adding this particles, whether it is microparticle or nanoparticle, increases the viscosity of the fluid. So pressure drop is increased, and these particles are larger in size, so the increase in pressure drop is considerably higher. And the last drawback is to increase the conductivity, we have to increase the concentration of these particles. So these particles are added either on weight basis or volume basis, say zero point 0.1 or zero point 0.5 or 1% by volume. So this the conductivity increases with the increase in the volume concentration of particles. Okay. So, but increasing the concentration of particles will result in settlement problem, erosion problem, and clogging problem, and so on. So, to overcome this drawbacks, we moved to the concept of nanofluids. Okay. Uh, the nanofluid is possible because of the advent of this scanning electron microscope in later part of the 20th century, so 1980, and the discovery of fullerene, also known as C60, carbon 60 nanoparticle. So these two inventions drove the development of this nanotechnology. So we have this technologies by which we can reduce the size of the particle from micro to nano. So this concept of using this nanoparticle was devised by Choi in 1995. So nanofluid is by definition a new class of fluids engineered by dispersing nanometer-sized materials, size less than 100 nanometers, nanoparticles, nanofibers, nanotubes, nanowires, nanorods, nanosheet or droplets. These are the different shape of this nanoparticles in base fluids. So you can see here, right? So this is the fluid, and the blue color represents the fluid, base fluid, and the green dots indicate the particles. And this bottom figure compares the different objects of different size. Okay. So insect size is 10 millimeter, and hair thickness is 100 micrometer, and blood cell is 7 micrometer. So whereas we have this nanometer, which is uh, 1,000th of micrometer, okay, or 1 billionth of a meter. Okay, so we are here, okay, less than 100 nanometers. Okay, something like the size of a DNA. Okay, the size of nanotube is around 1 nanometer. So it is much smaller, right? 1,000 times smaller than the micro size or the blood cell. Okay. So therefore, nanofluid is colloidal suspension of solid nanoparticles in base fluid water. So these are the commonly used base fluids: water, ethylene glycol, oil, and lubricants, and the nanoparticles, metals, metallic oxides, non-metallic oxides, phase change material, or functionalized nanoparticles. And these are the various types of nanomaterials. we can use in enhancing the thermal conductivity of a base fluid. Could be organic, filtering nanotubes like carbon nanotube, single wall carbon nanotube, multi wall carbon nanotube. Okay. And could be a bio material, organic material, inorganic material like metals, metal oxides, okay, quantum dots, or hybrid. That is, it could be used as a single particle or combination of these two particles like organic and inorganic, or inorganic and inorganic. So this is the photograph of nanofluid. Okay. So water, copper, and this is water Al2O3, and we have been using this nanofluid as a mixture of solid nanoparticles and basic kinds of fluid, and it is considered as a conventional nanofluid because there were some developments in the technology of nanofluid. As you said, uh, we have started using combination of this nanoparticles, either two particles or three particles or sometimes more, either added separately or in a composite form, like nanoparticles combination. Okay. That is this a kind of nanofluid uh, where the nanofluid consists of more than one nanoparticles. Okay. As I showed earlier, it could be a combination of this metal particles like copper, silver, or metal oxide particle like copper oxide, titanium oxide, like SiO2, Fe2O3, or carbon materials, or combination of any two or any three of these different nanoparticles like copper PiO2, or copper CNT, or ZnOCNT, and so on. So there were many research work goes on a single nanofluid, and this technology is receiving some greater interest or the significance nowadays, as it has been shown that, or found that these hybrid nanofluid particles have some enhanced thermal properties as compared to single nanofluid. And with respect to this nanofluid, we have the bodily fluid called blood. It is composed of blood cells, right, suspended in blood plasma. Blood plasma is liquid. Okay. So it accounts for 55% of the blood, and it's mostly water. 92% of this plasma is water. So blood cells like red blood cell, white blood cell, and the platelets, the solid particles are in suspension in this blood. So we can therefore consider the bodily fluid blood as a mixture of this solid particle and fluid. But this, of course, the size of this blood cell, as we have seen, is larger than this nanoparticle size, and so nanofluid is therefore, though it is a mixture of solid particle and fluid, since the solid particles are in very small size, so we consider it as the only fluid. And moreover, it is added in very low fraction, volumetric fraction, or the weight fraction compared to the volume or weight of the base fluid. So therefore, we have given the name nanofluid. Okay. So The advantages of a nanofluid is as the size of the nanoparticle is reduced, the specific surface area of the nanoparticle is increased. And in heat transfer, we know that when heat transfer surface is increased, heat transfer rate is increased. So by reducing the size from micrometer to nanometer, the heat transfer surface of the nanoparticle is increased. So better heat transfer therefore between these particles compared to micro size particles, nanoparticle and fluid, and compared to again this micro size particles, high dispersion stability, uh, predominant Brownian motion of particles. So it is a seamless motion of particles, which is due to the collision between the fluid particle and nanoparticle. So that motion is called Brownian motion, named after Brownian. So high dispersion stability is possible compared to the micro particles, and reduced pumping power. Okay. So even the pumping power, though the viscosity is higher and correspondingly the pumping power is also higher, the pumping power is reduced even when we compare to the pumping power requirement of pure liquid, pure heat transfer fluid. When the comparison is done for the same heat transfer capacity, because the heat transfer rate is considerably increased in nanofluid. So for the same heat transfer, if you compare the power requirement, will be more or less same, or even sometimes it is better for nanofluid, because obviously higher in terms of saving pumping power as compared to micro size particles. And then reduced particle clogging, and because the particle is very small in size, so it can flow even through micro channels. And then the properties of the nanofluid can be adjusted by adjusting the concentration of these particles, or by changing the size of the particle, by changing the shape of the particle. So we can customize therefore the properties as required, and we can use. So these are the advantages of nanofluid. Okay. So what is the effect of this nanoparticle on the thermophysical property of the base fluid? So when these nanoparticles are suspended in space fluid, they increase this convective heat transfer coefficient, increase the thermal diffusivity, increase the viscosity, and increase the thermal conductivity. How this nanofluid is prepared? So we have two different methods preparing this nanofluid. One is a single step method and other one is a two-step method. In single step method, the nanoparticle preparation as well as the mixing of this nanoparticle based fluid are simultaneously done. Okay. So the nanoparticles are prepared, are synthesized and mixed directly in the base fluid. So there is single step method. In one step, we do all the two steps preparation as well as mixing of nanoparticle in base fluid. The other method, two-step method, the two processes are done at different stages. In the first stage, we synthesize these nanoparticles, or we procure these nanoparticles commercially available. And then these nanoparticles are dispersed using dispersion equipment like magnetic stirrer or sonicator, homogenizer, with the basic transfer fluid. So this is a two-step method, and The one-step method is more suitable for metallic nanoparticles or nanofluid based on metallic nanoparticles, whereas the two-step method is suitable for non-metallic based nanofluids. This is a single step method. There are many methods, and I have shown here two methods. One is vapor deposition method, and other is laser ablation method. In both these methods, so this is the bulk material. Uh, so this nanomaterial, okay, in this vapor deposition method or laser ablation method is evaporated by heating the material. So this vapor goes into this fluid, the base heat transfer fluid, and the vapor gets condensed losing its heat to the fluid. So we have a cooling system to cool this fluid. So the nanoparticles are evaporated and condensed in the base heat transfer fluid. Similarly, in laser technique, the laser is bombarded upon this bulk material, the nanomaterial of which is to be mixed in this base fluid. So this is the solution. So this as a result of this laser beam and this particles are split into pieces, and these pieces get mixed with this base fluid. So this is single step method. So you can see here it involves the simultaneous production of this nanoparticles and mixing of this nanoparticles in the base fluid. So this is therefore a single step method. Whereas in two-step method, right, the required amount of the nanoparticle is weighed or measured using a weighing machine, high accuracy weighing machine, and then it is mixed in the base fluid. So for mixing, we use magnetic stirrer, homogenizer, or sonicator, either all three or any two, depending upon the material we use or the stability required. We prepare the nanofluid by this two-step method, which means we either use the nanoparticles available in the market or we synthesize this nanoparticle. So preparation is done ahead of this mixing, and then the mixing is done. So unlike a single step method where we do the simultaneous preparation of nanoparticles and mixing of nanoparticles, here they are done in stages. And of course, to improve the stability of this suspension of nanoparticles in base fluid, we use a surfactant or dispersant. For example, so this is the nanoparticle, the graphene nanoparticle. Then the distilled water is a base heat transfer fluid. Then this surfactant is also added to this mixture during the probe sonigation or homogenize process. Okay. So if we don't use this surfactant, you can see after the preparation of this nanofluid, this nanoparticle will get settled down. So because the nanoparticle will have the tendency to form clusters and agglomerates. So it will therefore forming large size particles and which will settle down by gravity. But when we use this surfactant, we can improve the stability of this nanoparticles. So the nanofluid will have good stability. So this is one of the important aspects of nanofluid. So we have to seriously consider this while prepare this nanoparticles. We have to do this stability study. So before we put the nanoparticle nanofluid into use. So this is about two-step method. Okay, the nanofluid possess enhanced thermophysical properties like density, specific heat, thermal conductivity, viscosity. Okay. But all these properties, right, influence this heat transfer performance of the heat transfer fluid, nanofluid, and the enhancement in these properties depends on uh, base fluid, type of base fluid, okay, whether we use water or oil or ethylene glycol, um, or additives like surfactants, and then the nanoparticles, the material, whether it is metallic, non-metallic, or carbon-based, then concentration of nanoparticles, size, and shape of the nanoparticle. They said, right? The size of the nanoparticle is ranging between 1 to 100 nanometers. And shape, it could be either a sphere or cylinder or rod or fiber. So particle may be same, but if the concentration is different or if the size is different, if the shape is different, it will have different influence on the nanofluid properties. Okay. So you can see, therefore, it requires a great amount of research to prepare the nanofluid of desired heat transfer properties. Thus, all these factors influence this thermophysical properties of the nanofluid and eventually the heat transfer performance of the nanofluid. So we have to therefore carefully consider and choose these various factors while we choose the nanofluid and prepare the nanofluid. So this shows how the nanofluid's thermal conductivity, right, is affected by different parameters like nanoparticle concentration, nanoparticle size, nanoparticle shape, nanoparticle thermal conductivity. Because metal has a high thermal conductivity and metallic oxide has low thermal conductivity. So naturally, if you add metal nanoparticles, the thermal conductivity of the base fluid is increased or higher compared to the nanofluid with metallic oxide nanoparticles. The base fluid type, nanofluid temperature, as temperature increases, this thermal conductivity increases, and preparation technique. Okay. So it depends how we prepare and how the stability of the nanoparticles over a period of time. So all these factors affect the thermal conductivity of the nanofluid. So similarly, viscosity of the nanofluid also depends on various parameters like viscosity of the base fluid, temperature of the fluid, then morphology of the nanoparticle, which is the shape of the nanoparticle, size of the particle, then shear rate, and volume concentration of nanoparticles. So one has to carefully consider all these performance influencing parameters so as to get the desired heat transfer enhancement. And so here the pressure drop of water, the base fluid or pure water, and the nanofluid is compared. So you can see the pressure drop of the nanofluid because of the increase in viscosity is higher than the base fluid. So which means the power requirement is increased because higher the pressure drop, greater the pumping power required. So larger the capacity of the pump is required. So this is when we compared for any velocity of this same velocity of the fluid, base fluid as well as nano fluid. Okay. But when we compare this with respect to the heat transfer enhancement, we'll find that the pressure drop is same or even less for this nanofluid sometimes. So there are some challenges of nanofluids. Okay. The common challenges are given here. The first challenge is nanoparticle dispersion agglomeration, and second is nanoparticle stability, then viscosity. Viscosity is increased, so increase in viscosity increases the pumping power, and in convection heat transfer, increase in viscosity affects the especially natural convection heat transfer. The Kirchhoff number is affected, reduced, so natural convection is inhibited, and the viscosity of the fluid, the heat transfer fluid, is increased. And the nanofluid cost is high because of these nanoparticles and the surfactant required. So cost of the nanoparticle is more, and the production of this nanoparticles is also to be scaled up. Okay. Because we so far we do it at laboratory level synthesis of these nanoparticles. So we have to improve this preparation of this particle source to different nanoparticles are available in the market. So among this challenges, this stability dominates. So we have to pay attention to this stability of this nanoparticles. Okay. So to improve or enhance the stability of nanofluids, we have different methods like physical method and chemical method. So in physical method, we use mechanical stirring or shear stirring, ultrasonic bath homogenizer. So when we prepare this nanoparticles by optimizing the time of this nanoparticle or nanofluid preparation, then we can ensure or enhance the stability of the nanofluid, or by using chemical methods by controlling the pH value of the base fluid, or adding surfactants, or modifying the nanoparticles called the functionalized nanoparticles. We can improve the stability of the nanoparticle, nanofluid, suspension of this nanoparticle in nanofluid. So that is the first part of the lecture. So we have seen the different types of nanofluids and preparation of this nanofluids, and the thermophysical properties of nanofluids and factors influencing the thermophysical properties, and challenges of nanofluids, stability of nanofluids. So let us now discuss the application of nanofluids in solar energy utilization. So if you look at the application of nanofluids, say in literatures, you'll find a very wide range of application of nanofluids. It says that it is used in different fields. I have shown here, right? Uh, since the topic is about solar energy utilization, right? It's used in solar thermal applications, in automobile applications, electronic cooling applications, medical applications, emergency applications, military applications. So this is only a sample list, but there are many more applications of nanofluids which you can find in the literatures. Because we are primarily concentrating nanofluid as a heat transfer fluid. Let us first discuss how this nanofluid is used in water heating, solar water heating applications. So, so one of the important components of solar water heating is solar collector. Solar collector could be either non-concentrating collector or concentrating collector. So nanofluid could be used in any type of collector. So to improve the heat transfer rate, the heat transfer that occurs within the heat transfer absorbing surface, which absorb the solar radiation, and then this absorbed solar radiation is transferred as heat to the heat transfer fluid. So by using this nanofluid instead of conventional fluid like water or a mixture of water and ethylene glycol, we can improve the efficiency of the water heater. So this is the classification of solar collectors. Be a non-tracking collector like flat plate collector, evacuated tube collector, compound parabolic collector, or one-axis tracking collectors like parabolic tuff collector or cylindrical tuff collector, linear Fresnel reflector, or two-axis tracking collectors like central tower receiver, parabolic dish collector, circular Fresnel lens. So this is the solar water heating system using this flat plate collector. So this is a thermochiffon system, so it uses no pump. So when water is heated, its temperature increases, so its density decreases, so it becomes lighter, so rises up, allowing this cold water or high dense water to enter into the solar collector. So this is a thermosiphon solar water heating system. The other one is active solar water heating system, where a pump is used to circulate the heat transfer fluid through this collector. And of course, any solar system requires a storage system to supply uniform heat, irrespective of the availability of solar radiation, like sunny day or cloudy day, or time, daytime, nighttime. So we can store this, okay, thermal energy in thermal energy storage systems. So solar flat plate collector, it is simply a flat plate. Underneath you have this heat transfer pipes, copper pipes. So these pipes are braced to the soldered to the absorber plate, black coated absorber plate, so that the solar radiation falling on this flat plate is absorbed, and the temperature of this absorber plate is increased, and this the absorbed heat is then transferred to the water flowing through this tubes across this copper pipes. Yes. And to prevent the heat loss from the bottom as well as sides, the sides as well as bottom of the solar collector are well insulated. So, so this is solar flat plate collector, and the efficiency of this collector is given by useful heat gain, which is measured by this MCP delta T, change in temperature of the water, into CP, specific heat of water, and mass flow rate of water divided by the heat input, which is the available solar energy. A into GT. A is the area of the absorber plate, and GT is the solar flux watt per meter square. incident on the solar absorber plate. So this is the characteristic curve of any flat plate collector. So instead of this water Al2O3, non-metallic oxide nanoparticle based water is used, and different size, different volumetric concentrations like 0.2% and 0.4% used. Particle size is 50 nanometer. So it is found that the efficiency of the solar collector is greater for this 0.2 percentage of weight fraction compared to 0.4 fraction. Okay. And the further when we use the surfactant, the efficiency is further increased. Okay. So then another nanofluid like multi-carbon nanotube water is used again for different concentrations like 0.4 and 0.2. But for this nanofluid, the increase in efficiency is higher for 0.4 percentage nanofluid. That's the 0.2 percentage reduces compared to water. So, so we have to therefore ensure that adding nanoparticles, like adding things, not necessarily improve the heat transfer rate, because adding any material to any heat transfer surface, solid material will increase the thermal resistance. So similarly, adding nanoparticles does not warrant any increase in heat transfer rate. So we have to, before putting this nanoparticles into use, we have to find the optimum concentration or the most effective concentration of nanoparticles through intensive research, through extensive experiments. But for 0.2 weight percentage of nanofluid, when we use surfactant, the efficiency is increased compared to water. So it is clear that for this multi-wall carbon nanotube, when the concentration is lower, the dispersion is not uniform or stable. Okay? So that is why when we use a surfactant, the suspension becomes stable, and the effective thermal conductivity as well as the heat transfer is increased, resulting in the increase in the efficiency of the collector. So, so the point to be noted here is the requirement of surfactant. Okay. So we have to therefore use suitable surfactant in the basically so it depends on the choice of surfactant depends on the material we use, the nano material we use. There are different types of surfactants: anion surfactant, cation surfactant, and amorphous surfactant, and so on. So we have to choose this surfactant carefully. And another important factor is the pH value of the solution, which is the measure of the hydrogen ions in the solution. It is quite important factor for aqueous solution like water. Okay. So it is experimentally found that the concentration of this counter ions, which are the determining ions, is zero at this isoelectric point, where the pH value, okay, the corresponding pH value has to be identified or measured first, okay, so that by keeping the pH value of the nanofluid, okay, either higher or lower than this pH value corresponding to this isoelectric point, we can increase the or ensure the stability of the nanoparticle. Okay. So as it said here, bigger difference between pH of nanofluid and pH of isoelectric point leads to higher efficiency, higher stability, and higher efficiency, because the nanoparticle has to remain in suspension over the period of usage of this nanofluid. So if these nanoparticles get settled, then it will become simply base fluid, a normal fluid or ordinary fluid. So the effect of this nanoparticle is not felt. So we have to therefore ensure that the stability is ensured or increased in order to improve or enhance the heat transfer performance of any heat transfer systems. So again, this comparison shows, I said the pH isoelectric point is 7.4. So you can see here this is for 6.5 pH value, and this is 3.5, and this is for 9.5. So this is this pH value is close to this isoelectric point. So as move we further away from this pH value corresponding to isoelectric point, which is 7.4. So the enhancement in heat transfer and the efficiency of the collector is increased further. Okay. So this, the effect of this particle size on efficiency is also studied. So the increase in particle size, the efficiency of the collector decreases. Okay. And the different researchers have obtained different results. So some researchers have obtained that the efficiency of the collector increases with the increase in the efficiency of the particle diameter. Here, this researcher has obtained the nanoparticle size increases, the efficiency of the collector decreases. So that is about flat plate collector. The other one is vacuum tube solar collector. So to improve the efficiency of the collector further, okay, so this vacuum tube solar collector was developed. So it consists of a double wall tube. And the inner wall of the inner tube is coated with some good absorbing material. And at the center of this double wall tube, we have this copper pipe. So either we can use this water to be heated directly in this inner tube, or we can pass this water through the tube, or we can use this copper pipe as a heat pipe, so that when this cold water enters into this tube, it is heated by the particle solar radiation, whether it is heat pipe based vacuum tube solar collector or direct heating vacuum tube solar collector. The water is heated, so it becomes vapor. So vapor moves, right, by virtue of this density difference upward. So, but the important advantage of this collector is because the heat transfer surface is completely surrounded by a vacuum pipe, glass pipe. Okay. So there is no fluid in between. So convection heat transfer is reduced, and conduction heat transfer between this tube and the surrounding air is reduced. So heat loss is minimized as compared to flat plate collector. So the efficiency of this collector is, though it is costlier, higher than the flat plate collector. Okay. So the efficiency of this collector was experimentally studied using nanofluid, water TA wood and water carbon nanotube nanofluids. It was found that the carbon nanotube based water nanofluid has very good high heat and conversion characteristics. So the temperature of the water obtained from this nanofluid CNT nanofluid is higher than that of the titanium oxide based water. So this study confirmed that CNT-based nanofluid, water nanofluid, is more suitable for vacuum tube solar collector applications. And another type of solar collector is direct absorption collector. Okay, so here there is no heat transfer surface. The water is directly heated, exposed to the solar radiation. So this water absorbs the solar radiation and becomes hot. Something like the water in sea or river or ocean becomes hot during daytime as it is continuously exposed to this solar radiation. So here the heat transfer network or thermal resistance network of the two collectors is shown here. Okay. This is the conventional or the normal flat plate collector. So you have absorber, okay, plate, but here there is no absorber plate. The working fluid is directly heated by the solar radiation. Okay, so it has just only two thermal resistance, but here it has two more additional resistance. So naturally, or obviously, the heat transfer rate is increased. Because the lower the thermal resistance is involved, higher the heat transfer rate. So application of nanofluid is tried in this direct absorption solar collector. So instead of using just water, we can use carbon nanotubes like water, aluminum nanoparticles, and the volume fraction of zero point 0.1 to zero point 0.5. Efficiency was found to increase remarkably for low values of volume fraction. Okay. So the difference between this nanofluid and base fluid is because the presence of nanoparticle increases the absorption of incident radiation. Okay, so this particles absorb the radiation, solar radiation. So the heat transfer is therefore increased. It is 9 times that of the pure water. So efficiency is therefore increased by 10% as compared to flat plate collector. And this shows how this uh, efficiency varies with particle size and volume fraction. Okay. So as particle size increases, collector efficiency increases, as against the previous results for flat plate collector where the particle size increases while efficiency was decreasing. Then this the collector efficiency increases as volume fraction increases, say up to around 1%, and then thereafter there is no much increase in the efficiency. So this graph shows that the optimum size of particle and optimum volumetric fraction of particle we can use in the actual system. So before we use this nanoparticle in any system, we have to do, right, good number of experiments by varying the size of nanoparticle or the concentration of nanoparticle, for which the heat transfer rate is maximum, or thermal conductivity enhancement is maximum. We can use it in the solar system. So this is another study where carbon nanotube, graphite, and silver nanoparticles are used in base fluid. Okay. So the silver nanoparticle has nanofluid based silver nanoparticle has maximum efficiency compared to CNT or graphite. And then solar concentrating collectors. So in the previous types of collectors, the solar radiation is not concentrated. Okay. It is used as it is received. But we have concentrating collectors like parabolic trough, linear Fresnel, then paraboloid or dish type collector, and central receiver type collector. Okay. So in these collectors also we use heat transfer fluid. Okay. So these are the receiver pipes. Okay. The parabolic trough. This is the receiver absorber pipe tube for the linear Fresnel system, and this is the receiver, okay, of this paraboloid collector, and this is the tower concept or central receiver. The absorber is located at the top of the tower, surrounded by this mirrors or the heliostats. So this shows the solar concentration plants, how this collectors generate this or convert this solar power or solar radiation into thermal energy. Okay. So this is a parabolic trough collector, which uses a reflector and a receiver tube or absorber tube. The absorber tube is located at the focal point of this parabolic trough. So it is a line focusing collector. So the incident solar radiation, especially direct radiation falling on this reflector, is reflected onto this receiver. So that is how the solar energy is concentrated. So these are the four important types of concentrating collectors. So solar energy falling on large area is concentrated on a smaller area. So the concentration ratio is defined as the ratio of the absorber area to the aperture area, the collector aperture area to absorber or receiver area. Okay. So normally the aperture area is it is the projected area on a horizontal plane. So it's much higher than this receiver area, absorber area. So concentration ratio of this concentrating collectors is normally high as compared to flat plate collector. For flat plate collector, the concentration ratio is 1 because the aperture area or observer surface area as well as the receiver area are one and the same. So concentration ratio is 1. Okay. So the concept of this using nanofluid in concentrating solar collectors have also been tried. So it was found that the use of nanofluid in receiver improve the efficiency of collector by 10% when compared with conventional concentrating solar thermal systems. Okay, the nanofluid used is graphite because this is a high temperature system. Because of concentration, high temperature can be achieved, right? More than 100 degrees Celsius up to very large, very high degree Celsius, 400, 500, even higher. Use oil as the heat transfer fluid terminal, so one of the heat transfer oil used in concentrating collectors. So graphite is the nanoparticle added to this terminal in the volume fraction of 0.001%. So this picture shows, okay, so by using nanofluid instead of conventional fluid in concentrating systems, we can improve the efficiency of the collector by say 5 to 100%. So this graph shows the enhancement in efficiency. So this dots show the efficiency of ordinary concentrating collector, parabolic collector, and this show the efficiency of the nano fluid based parabolic trough collector. So that is about solar thermal collectors. Another important application of solar energy is converting solar energy directly into electrical energy using photovoltaic cells. So a single cell, it is a semiconductor device, can generate zero point 0.5 to 1 volt in the current density of 20 to 40 milliamps per centimeter square. So this is the arrangement of the cell. So we have a P-type silicon and N-type silicon, and PN junction in between them. And the top side of the cell, we have this metal contacts in the form of fingers, metal fingers, and at the bottom we have this uh, metal contact which completely covers the bottom side of the photovoltaic cell. So when a light energy falls on this semiconductor material, and when the light energy is more than the band gap energy, the electrons are excited, so they are able to now move across this PN junction. So from P-type junction to P-type semiconductor to N-type semiconductor, so resulting in flow of electrons. So when you connect this solar cells to any load, you have this current flow, okay, from P to N. So the important factor affecting the efficiency of this solar cell is the temperature of the solar cell. Okay. Because they are constantly exposed to the solar radiation. So the temperature of this solar cell increases. So there was attempt to reduce this temperature of this solar cell so that the temperature of the solar cell is maintained and the performance of the solar cell is improved or increased. So we have therefore the bottom side provision for the flow of fluid, nanofluid. Okay. So this fluid and with the enhanced heat transfer, the characteristics, okay, when it flows through this channel, like absorbs the heat generated due to the incident solar radiation. So it was found that the rate of cooling increases with increase in volume fraction. Okay, for different Reynolds number, as Reynolds number decreases, okay, the average modified Nusselt number increases, and when the Nusselt number increases, rate of heat transfer increases or rate of cooling increases. Okay. So when the temperature of this therefore photovoltaic cell is kept under control, the efficiency of the cell is increased or remain unaffected by the increase in temperature of the solar cell. Okay. The other application we can use the nanofluid as also as an optical filter. Okay. Optical filter in the sense, so the nanoparticle having good optical properties will filter out this unwanted wavelength of solar radiation. Okay. That is, it prevents the radiation which are outside the required range of wavelength, while allowing the desired range of wavelength to pass through. So they are used as optical filter, as well as by absorbing this solar radiation, they become hot. So they are also therefore used as a coolant here. Okay. So we therefore, besides generating this uh, solar cell, we can also generate thermal energy. Okay. So simultaneous generation of this electrical energy and thermal energy is possible with the application of this nanofluid. And these are some of the future works. Okay. Still, there is much more work need to be done with respect to the collector, okay, especially the parabolic trough collector and the photovoltaic thermal systems. So still a lot more work has to be done. And another application of this nanofluid is solar still. Okay. We know that the scarcity of drinking water increasing day by day. Okay, nearly 2.8 billion people currently have no access to the safe drinking water. So we can use this solar still to produce this fresh water from the salt water. So these are the different solar stills used to generate potable water, like single basin system or a single slope system or a double slope single basin system. So it works on the principle that the two important principles, evaporation and condensation. So when what solar radiation strikes this bottom plate coated with some good absorbing materials, absorb the solar radiation, and this the temperature of the plate is increased, so which in turn is transferred to the water over the plate. So the water is heated, so it is evaporated, and the vapor when it rises above, right, comes in contact with the cooled glass plate, because the glass plate is transparent to the incoming radiation. Okay, so almost 95% of the radiation is transmitted. So the temperature of the glass plate remains right much lower than the temperature of the bottom plate or water vapor. Uh, so the water vapor gets condensed on this glass plate, and these glass plates are inclined, okay, downward, so that this water condensed water right, flow down this glass plate, okay, collected in this water collection trough or gutters. So this is a pure water. Okay. So by adding this nanoparticle to this brackish or salty water, it's found that the rate of evaporation is increased, and hence the efficiency of the solar still is increased. By carbon nanotube is used, it was found that the efficiency was increased by 50%. And of course, here there is no loss of nanoparticles, so we can recover the nanoparticle, right? Or use the nanoparticle again and again uh, for the preparation of this nanofluid. Then another application of solar energy is solar pond. So it was found that in some natural lakes, that because of this salt availability at the bottom of the lake, the bottom of the lake, the water at the bottom of the lake remains hot, and the top water layer remains cool. Normally, when water is heated, it tends to rises up by virtue of this decrease in density. But here, since the water is salty water, because of the naturally uh, salt rocks available at the bottom of the lake, the water is salty at the bottom, so the density of the salt water is higher. So though the temperature is increased due to the absorption of the solar radiation, it remains at the bottom. So that technology or this mechanism is used in this solar pond. So we have three different layers: low temperature or low concentration layer, gradient temperature or gradient concentration layer, and the bottommost layer is called high temperature or high concentration layer. So upper concentration zone, uh, non-convective zone, and lower convective zone, okay, are the three different zones of this solar pond. Okay. And by maintaining some different salt gradients, okay, we can maintain the hot temperature fluid at the bottom, okay, as compared to the temperature of the fluid at the top. Okay. So this the solar energy collected by this bottom layer then could be extracted. So for this, we can use these are the major salt gradient solar ponds available in India. In Bhuj, we have an area of 6,000 meters square, okay, depth 3 meters. So these are the solar ponds. Okay, so where we use this either nanofluid directly mixed with the salt water in the pond. It requires large quantity of nanoparticles, or else we can use this nanofluid to absorb the heat stored in the uh, solar pond. Okay, so solar pond is a collector as well as a storage device. It collects solar energy as well as it stores the solar energy. So the stored energy can be retrieved using this nanofluid. So we have seen some of the applications of nanofluid in solar thermal systems like solar collectors, rapid collector, direct absorption collector, uh, concentrating collectors like parabolic trough collector, and then solar cells, solar stills, and solar ponds. There are many other applications. Because of the time limit, we cannot discuss the applications of nanofluid and other systems, solar systems. But the challenges of this are high cost, uh, high pumping power, high pressure drop, instability and agglomeration, erosion and corrosion. So, the two important considerations of economic and environment consideration. Naturally, the nanofluids are expensive because of this nanoparticles requirement and addition. So capital cost of the nanofluid is higher, and maintenance cost is also higher because we have to ensure that the nanofluid stability. So, but greater fuel cost saving per year because of the higher efficiency and angular solar fraction. Because using nanofluid in these solar systems improve the efficiency of the system, so which will save greater fuel. And, but since the cost of the nanofuel is higher, the payback period of the solar systems using nanofuels is longer. So that is about economic consideration, and environmental consideration is nanofluid use results in lesser emission of this carbon dioxide because the effectiveness of the system is increased. So for the same heat capacity or generation capacity, we need a smaller size solar systems. So manufacturing of the smaller size systems and operation of these systems results in savings of this greenhouse gas carbon dioxide. So nanofluid based solar collector emit right 700 kilogram of carbon dioxide, less than conventional solar collector would emit over a period of its useful time or useful year. Normally, 15 years is the right useful life of solar collector. Okay. So, I'd like to conclude my lecture saying that there are many points which go in favor of this nanofluids as compared to against the use of nanofluids, because the properties like thermal conductivity, thermal diffusivity are enhanced, and hence the heat transfer coefficient is also increased. Okay. So, which enhance the thermal conductivity of the nano fluid, and overall the heat transfer performance of the nanofluid is increased. But as I said, right, yeah, the thermal performance or the thermophysical property enhancement depends on a number of parameters, like the concentration of this nanoparticle, size of the nanoparticle, shape of the nanoparticle, uh, then base fluid, type of base fluid, then temperature of the fluid, and then the surfactant used. So these factors therefore affect the enhancement of the thermal conductivity in nanofluids, which ultimately affect the thermal performance of any heat transfer system, whether it is a solar system or any system. So, which requires, right, more intensified research to consider the issues like synthesis, characterization, thermophysical properties, heat and mass transport, modeling, and device, as well as system level applications. So, which requires a multidisciplinary approach, uh, comprising researchers from chemistry, physics, material science, then mechanical engineer, electronics engineer, because the role of electronics engineer is important in electronics cooling. So that requires a multidisciplinary approach. So by doing this multidisciplinary approach, so we can ensure that the nanofluid characteristics are improved, and we have a sustained enhancement in performance of the solar systems or any systems for that matter. So ensure that the nanofluid will emerge as a better fluid in near future. So there are many research works, investigations on this nanofluid, which are at laboratory level or research level. And, only a few found application of this nanofluids in real time field. But in near future, this nanofluid will prove to be a potential fluid in any cooling applications. So we'll have a cooler future with nanofluids. Okay. Thank you. Thank you for your kind attention. If you have any queries, you can raise your queries.
Participants, sir.
Yes, yes.
I will read first question, sir. Asking from Mr. Dinesh Babu. Which nanomaterial is widely used in solar PV panels for enhancing the efficiency?
See, we cannot say any specific nanoparticles. That is what I am saying. A multidisciplinary approach is required, or more intensified research is required. In the sense, we have to do a lot of research before we choose the particular nanomaterial. Okay? Because each nanomaterial has its own thermal conductivity, and when it is mixed, the effective thermal conductivity enhancement is different for different nanoparticles. So we cannot say which is more commonly used. Right? They are all at research level only. Whatever content I have shared with you is research level work. Okay? So we have to do a lot of research before we use this nanofluid in any particular application. So we can use any nanoparticle, as I said. We use solid nanoparticle because they have higher thermal conductivity. The effective thermal conductivity of the nanofluid is going to be higher compared to any other metal oxide. Or if you use some carbon-based nanofluids, because the thermal conductivity of graphene or carbon nanotubes are few thousand, so they are much higher than even metals. So the effective thermal conductivity enhancement could be sometimes even 200% more than the thermal conductivity of the conventional fluid. So it depends on the application and more intensified research to choose a particular nano fluid or nano material.
Okay, sir. So next question from Mutturasu from GPTC Tuticorin. By using nanoparticles, how much thickness of the plate is possible?
No, whatever I have discussed here, there is no change in the basic system. Right? The conventional system, whatever we use, we can use nanofluid. Okay, there is no system modification is required. Instead of base heat transfer fluid or conventional heat transfer fluid, we use nanofluid. So no change in the size or dimension of the any heat transfer components. So they remain same. Only the changes in the heat transfer fluid, because the thermal conductivity of the fluid is increased, the heat transfer rate between the plate, absorber plate, or any heat transfer surface and the fluid is increased.
Okay.
So there is no change or the dimension of the system used for both nanofluid as well as conventional fluid.
Okay, sir. Next question from Alagappan Narayanan. How long the nanoparticle is stable?
Question, right? We cannot decide, right? Or even come to a decision how long, right, it will be stable. We have to ensure that, right, the through physical observation, right, the fluid is stable. But what I suggest is, after the preparation of nanofluid, we normally do a study called zeta potential test, so which measures the electrical potential of the double layer, diffuse double layer. So higher the zeta potential, higher the stability. So we have to repeat this study after immediately after preparing the nanofluid, and say after 1 month or after 6 months, after a year, to see that there is no change or there is little change in the zeta potential. So which means if this zeta potential value remains uniform or approximately uniform, or the change is not much, which indicates that the nanofluid is stable. So you can use this nanofluid. So the point is, before we use the nanofluid in an application, we should measure the stability of the nanofluid over a period of time. Because if you refer any literature, in some literature there is no stability report, study analysis is given. In some other literatures, the zeta potential measurement after the preparation of nanofluid is given. But the question is, will it be same? Will the stability be same after some time the preparation of the nanofluid? So to check this, we have to repeat this stability measurement test. Either we can do it, or we can even observe it physically to see whether there is a change in the stability of the fluid. Because if there is any stability of the nanofluid is not good, weak, it means these particles will settle at the bottom. So you will have a clear fluid, right, at the top. Okay.
Okay.
So
So next,
superconductant fluid.
okay, sir. Next question from Kanagar Raja. Is it any possible to use engine cooling system?
Yes, yes, that is one of the important applications of nanofluid. You can use this nanoparticles in conventional engine cooling systems used in radiators, automobile radiators. So we use some water glycol mixture as the coolant. We can add some nanoparticles, right? Either metal nanoparticles or metal oxide, or there are many research works done on this. So you can very well use this, right? Even nanoparticles are added to this fuel, diesel, right? To increase or enhance the performance of the engine by improving the rate of combustion. So there is a wide range of applications of nanofluids.
Okay, sir. Next question from Mr. Alagappa Narayanan. For 0.2 percentage weight nanofluid, how much ml of surfactant will be added?
No, this, again, the surfactant will be the quantity of surfactant required will be determined based on the particle concentration. For 0.2%, either we have to use 0.1 or 0.2 percentage of the volumetric concentration of the nanoparticles. So based on the volumetric fraction of nanoparticles, we have to choose this concentration of surfactant. Okay. So again, the performance of this nanoparticles, nanofluid depends on the concentration of nanoparticles. Similarly, the performance is also affected by the quantity of surfactant used. So we have to therefore do some experimental study to determine the optimum ratio of this surfactant and nanoparticle. So how we vary these nanoparticle concentration. So in the same way, we have to vary the surfactant also.
Okay, sir.
So based on that, we have to find out the optimum ratio of surfactant and nanoparticle. Okay.
Okay, sir. Last question from Tangarasu. What control measures of pH value in nanofluids?
pH is a measure of the uh, hydrogen ions in the solution. So these when the nanoparticles are dispersed in this aqueous solutions, surface charge density is created. For example, if the surface charge is negative, so the positive ions of the fluid will be attracted by this surface. So you will have this positive ions surrounding this nanoparticle, and then this will be surrounded by the charge determining ions, the negative ions, and then this positive ions are, and so on. So the potential, right? Zeta potential is the electric potential measured at the diffuse layer, the slipping plane of the layer, which will move along with the nanoparticle. Okay, when nanoparticles they are in constant motion in the nanofluid. So the plane at which this nanoparticles, the ions surrounding the nanoparticles move along with the nanoparticles, the potential at that point, this plane is measured. So that potential is called zeta potential. So for the pH value for which the zeta potential is zero, is the isoelectric point. Okay, so we have to determine this point first for any nanofluid, okay, and maintain the pH value sufficiently away from this pH value, either plus or minus above this pH value or below this pH value. So we can ensure the stability of the nanofluid for sure. So we have to find first the pH value having zero zeta potential. So that point is called isoelectric point. So that is the point at which the potential is zero. Okay.
Okay, sir. Thank you, Dr. Valanus, sir, for
Yes.
accepting our invitation and give wonderful presentation to audience, sir.
Yes.
Once again, thank you, sir. Thank you for all the participants.
Thank you. Thank you.
A warm evening to all the participants. It seems to be great honor in proposing this vote of thanks to all who have assisted us in making this webinar a responding success. On behalf of Francis Xavier Engineering College and the entire fraternity of the college, first of all, I extend my most sincere thanks to the Almighty for making this event possible. Now, I extend a very hearty vote of thanks to our Honorable Speaker Dr. A. Valanarasu, who spared time from his busy schedule to grace this event. Thank you for your thought-provoking and fascinating talk on nanofluids in solar energy utilization. My sincere thanks to you, sir. I also extend my genuine thanks to the management, respected General Manager Development, Dr. Jayakumar sir, and our beloved Principal Dr. Velmurugan sir, without whose help and guidance the program would not have been a grand success. Behind every success we attain live the manifold efforts of our committed faculty. I would also like to take a moment to thank our HOD, Dr. Joe Patrick sir, Dr. Zinatul Farida Abdul Kani ma'am, Dr. I. Needhi Monikam sir, the event coordinator Mr. Ayana Raja sir, and all other faculty members associated with this event for their genuine support and wonderful leadership in conducting such a productive program. Finally, I like to place on record my sincere gratitude to all the participants for your outstanding involvement. Thank you all.